Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving here today, as it is every day here in my virtual classroom. Alright, step on inside for the Big Ideas Math, Integrated Math 2, folks. We are looking at a Chapter 1 review, covering sections 1.1 to 1.6 on, let's see if I can remember them without reading them here, on absolute value functions, piecewise functions, inverses of functions, properties of exponents, radicals and rational exponents, and exponential functions. We are going to get a series of 33 problems laid out from, I think they're in order, I think they're all kind of detailed that way. They show 1.1 with some examples, and then some problems, and then 1.2, etc. That's how this will go. And if you haven't seen any of the videos and any of the lectures before, check out the description section below, and you'll see a playlist of the whole Integrated Math 2 stuff that we've done so far, specifically for Chapter 1. And there was a 1.1 to 1.3 review. This is a Chapter 1 review for all of them. Coming up next in this video series would probably be what is the Chapter 1 test. This is all in the textbook, by the way. There's a PDF of these pages down below. I'm prepared with a calculator just in case, and I'm prepared with graphs that I need to draw and such just in case. I have not seen the problems myself, so we'll see what these all look like together. For the most part, I've taught the material in the past, so I'll uncover what they say in the examples, and hopefully that's enough to speed through the rest of these, and it should be good. But check out timestamps if you want to find very specific sections there. So let's go ahead and take a look at what we have. And what we have here, here's what I get to write on, is in 1.1, absolute value functions. They're showing examples, I think, right here, and then we'll do these problem sets. So let g of x equal negative 3 times the absolute value of x plus 1 plus 2. That is the red one here. Describe the transformations from the graph of f of x equals absolute value of x, the black, to the graph of g, and then graph g. So I think that that blue and that green are in between to state everything that happens in between, and we'll go ahead and see those when they do that. I'm surprised they mentioned translation first, but because it's horizontal, it's okay. So from the black, they first ask you to translate the graph of f horizontally 1 unit to the left and get this t of x, which I don't see on here because it's not stretched yet. Then they stretch the graph, and then you get this one that's in, oh, I guess the black is that one that's translated. So the parent function's not here. Here's t of x in black. Blue is when they vertically stretch this thing. So before, when you'd go up on 1.1, now you go up 3 over 1. And that's a vertical stretch by a factor of 3. Then they reflect it over the x-axis to make the blue turn into green, so it goes upside down. And that's when they translate up afterward. So I generally save translations for last in general, because translations up and down get affected if you reflect last. So you got to or stretch last. So you got to reflect first and stretch first in general. They say make a table of values. We use the give me a second. We use this here. Vertex form of an absolute value function. So A is your vertical stretch factor, H is your horizontal translation, K is your vertical translations. You've seen it in my previous videos, hopefully. So I'm going to be referring to that more so than using a table. Plot the ordered pairs, draw the graph. It's going to be the one in red. Okay, so that's an example of one. We'll go ahead and start our own set on this problem. Numbers 1, 2, 3, and 4, maybe all of these. Graph the function. Compare the graph to the graph of f of x equals absolute value of x. Describe the domain and range. So by comparison, I will describe those transformations probably in less steps. But let's go ahead and see what we got. So on number 1, we have m of x equals absolute value of x plus 6. Now when you refer to that, once again, this vertex form of an absolute value function, I want to identify what a, h, and k are, and that will allow me to graph this in general. A still seems to be 1 based on what we've looked at. H looks like it's 0, x minus 0 is going on, and k is 6. The only transformation that appears to be happening is we are translating 6 units upward from the original graph. So that's all I'm seeing on this, and we'll go ahead and sketch this thing. Now they say compare it to the absolute value of x graph. I don't think I'm going to draw that one on there. I'll just stick with the new one that we're doing. So absolute value of x plus 6, we go 6 up to here for the vertex, and then it's still a rise and run of 1 in both directions to make the V shape of this graph. Like so, without actually using a table, but you could and get those points. And give me a second, I'm going to go ahead and connect the dots like that. Okay, there's the graph on that. Now they're asking us to also move this a little bit. Give me a moment. Okay. There we go. They're asking us to also describe the transformations. Or that's kind of what we're doing here. It's basically translate 6 units up. There's nothing else that's happening. No reflections, no stretches, no horizontal translations. And that'll be it for number 1. Number 2. P of x equals, and it looks like they're only doing one at a time. I kind of wish that they did. Oh, they probably do that in 5, 6, and 7. Number 2. P of x equals absolute value of x minus 4. The minus 4 is inside of the absolute value this time. This time, as a stays as 1, now h is 4. Remember that it's x minus h, so it's x minus 4. H is 4. And k is 0. That means there's only a horizontal translation this time compared to the previous one, which had only a vertical translation. So instead of starting at the origin, we start at 4, 0. Still a rise and run of 1 like so. No change in vertical stretch and no reflection. So like that, and then we'll connect our dots. Okay. And then we will translate 4 units right. Now, they say a little bit more. They say translate F and such. Fine, translate F 4 units. Nah, that looks weird. 4 units right. Remember, it's from the original, where it starts at the origin. Okay, number 3. Q of x equals 4 times the absolute value of x. Getting a scam phone call. That's what my phone says. It says scam likely. If you hear the vibration, I apologize. It'll do it just for a second longer. Okay, this time only a changes. H and k are 0. The a value is 4. That's the value that multiplies in front. This represents a vertical stretch. That's what's being affected this time. So we have our graph, f of x, instead of going up 1 over 1, it goes up 4 over 1 for a vertical stretch. We vertically stretch this guy by a factor of 4. Starting at the origin. So from here, up 4 over 1, up 4 over 1. Everything's 4 times taller than it was before. Like so, but once again, it's at the origin, like that. So I can say vertically stretch. It's not just stretch. There's horizontal stretches as well, which I generally try and avoid. But we'll see. By a factor of 4. And lastly, number 4, not lastly, but of these basic ones, I suppose. R of x equals, 2 transformations technically, negative 1/4 times the absolute value of x. Oops. I was looking at these letters, M, P, Q, and R, M, N, O, P. They skipped N and O. I don't know why I don't know my alphabet. They skipped N of X and O of X. I kind of understand O of X. I don't know why there's no N of X. Okay, so with this last one, A is negative 1/4. I might have to sneeze. The 1/4 would be up 1 over 4, up 1 over 4, but we go down 1 over 4 from the origin, by the way, because it's reflected over the x-axis. So those are 2 different things that we're going to have to describe. There's a vertical compression. I believe the book tends to use the phrase shrink, vertical shrink. So we'll take a look here. They might even say, because I'll bring it up in a bit, but they might even talk about a horizontal stretch. It's unlikely. So vertically compress by a factor of 1/4, but also reflect over the x-axis. Now, I probably should have said the reflection first. That actually doesn't matter, but I like to go from left to right. So the negative has to do with the reflection. The 1/4 has to do with the compression, and everything else is the same from the origin, and that would be that one from the original graph. So those are the first 4. Okay. Now we go to number 5, where we are graphing 2 graphs together, and we have to compare the 2 and what they do. I felt like I had a lot of trouble on these when I was kind of answering them the first time because I wanted the order to be right. So let's see if I can kind of get this one correct here. So we use blue and green to compare them. I got f of x equals absolute value of x minus 2 plus 4. And then we have g of x equals absolute value. Oh, hold on. This is one of those examples I might refer to horizontal stuff with you guys here. I'll do what I did before, which was, I don't know if it might have been confusing. Now that I go back to it, if you go to my section 1.1 video and you run into graphs that have a number in front of x, I talked about factoring things out. If you're in integrated math 2, you don't learn factoring until chapter 2 and later the latter half of chapter 2. And I noticed when I was tutoring, I just want to say this quick, I noticed when I was tutoring other students for integrated math 3 stuff at my school, their book, the Big Ideas math book for integrated math 3, was talking about transformations and using things inside of here and really talking about horizontal things, which they are. I just didn't know that that's how it would be described, because I don't like using a table for my graphs for vertex form and such, and I have to do a factorization. So I might be a little hit and miss with regard to the explanation. We'll see how it ends up working out, because there are two different ways you can describe this. So as far as the graph of the blue itself, this is 2 right and 4 up, and it looks like that. That's the vertex. And then you rise and run 1 like this. Now, there's only one, if you do this right, this is probably why I had so much trouble with the transformations, and this is what they wanted us to do. The easy way to describe this next transformation on green, and I don't want to spend too long on the idea, even though I'm teaching it for the first time, is you remember how these have the x minus h plus k stuff. There's a times the absolute value of x minus h plus k. Well, if you notice that h on the inside is subtracted instead of added, because it's all about what do we substitute for x to offset the fact that something's if h is 4, or x minus 4, that means I have to plug in 4 for x to make this 0. So it's opposite of. So instead of referring to a on the outside, if you had some, this is what the book says in IM3, some 1 over a on the inside, then these are what are horizontal stretches and compressions. But it's inverted, because you need to make x a times larger to offset something that is out here to make it smaller. My point is, when you see this 3 is also 1 over 1/3. That means the a value is 1/3, but it also is referring to, sorry, as far as 1 over a goes, but it also refers to the fact that you are not stretching this thing 3 times, you are compressing it 3 times horizontally. And I think they use the letter A, at least that's what someone said in notes. I'd rather use the letter B and have a different one, so I probably will do that. Again, this is me doing this on the fly. I apologize. This is not how I would generally do this. And even more so, I'd have to factor it out for this to be the true H for your vertex. There's a lot of things I have to talk about here for this kind of problem, but this is where it goes about. So again, if you're watching it, it's based on whatever your teachers say. I generally don't use this part, but I have to factor it out to make it work for proper vertex. Otherwise, like they said, use a table. So what's my point of all this? The B is 1/3. That's something inside of here. You need to horizontally compress this graph. You need to make x's that are 1/3 the size of what they would normally be. Horizontally compress by a factor of 1/3. Now the graph itself, I'm going to draw the graph in a bit, but I'm going to use my graphing form when I factor this out and give 2 different versions on how this can be stated. That's one way you can state this, like that, or, and then we'll get to the other one after I do the graph that has to do with what happens when you factor this thing out. So, excuse me, what's the whole factoring bit? We look at g of x equals absolute value of 3x minus 2 plus 4. I'm going to factor 3 out, which is the opposite of distribution. It means when I pull 3 out of here, what would I have to distribute? Excuse me. What would have to be inside of here for me to distribute 3 into here to get 3x? 3 times x would give me 3x. And 3 times what gives me negative 2? That's the little trickier part. That's negative 2/3. 3 times negative 2/3 is negative 2. And the other tricky part is we got to draw this graph. Now that 3 that I pulled out of there is, once again, the 1 over b thing. That's why b is 1/3. But I'm going to pull 3. I've mentioned this in the past. The 3 out of here. The absolute value of 3 is 3. So it can come on the outside like that. Like so. So I'm going to graph it like this. This is my A, H, and K. H is 2/3. It's not a very pleasant value, but this is how I'm going to deal with it. H is 2/3. K is 4. So over 2/3 up 4. And then I will rise 3 and run 1. Rise 3 and run 1 like this. And rise 3, run 1 to the left like so. So without actually using a table, these points aren't beautiful, but they do work as points. And I'm going to go ahead and draw that. So the real question is, how do the graphs compare? And the answer just came right here. You horizontally compress by a factor of 1/3. Keep in mind that even the vertex got compressed by a factor of 1/3. Before it was at 2, now it's at 2/3. That's a third of the size of what it was. And everything else compressed. Instead of up 1 over 1, I know you see this as up 3 over 1, but it's also up 1 over a third. Up 1 over a third and up 1 over a third. That's what makes that a compression. So that's one way. That's the way they'd probably want you to describe it based on what I've noticed and what I've been tutoring. That is messy. The alternative is what I just did, making the equation look like this and stating it based on that portion of the equation, which is weird. I start to do weird translation things with this. I'd say vertically stretched by a factor of 3. This is what you saw in my previous videos, and this is where Mr. Robinson's virtual math classroom might not be the best way to go with this. Your teacher is going to say, what is going on? Vertically stretched by a factor of 3. And also translate. See, this is the weird part. 4/3, 1 1/3 units to the left. That's only when I'm comparing the... Oh, shoot. Hold on. This will be a little confusing. This is where something did get confusing when I mentioned it. But vertically stretched by a factor of 3 and translate 4/3 units to the left. I forgot what I was mentioning before. But this is the problem of this one. This is where I think I was doing it wrong, and I probably am. If I make it vertically stretched, that means this should go from 4 to 12. So this thing's a little off. I wasn't great with answering these before. I'm still not. That's why this is the correct answer. And they want you to use a table. So the book sets it up in a certain way. I like the graphs the way that I do. Sorry if it's a little incorrect. That's just how I go about it. I just hope that there's not more to it than that for those kinds of questions, because I feel uncomfortable answering them for you versus a method that I'm very comfortable with. All right, number 6. I know that's not great. Describe another method you can use to graph G in the example above. I wonder if that's what they're talking about, which is getting this into this vertex form. That's kind of my other version. Their first method is using a table, right? So if method A is use a table, like they probably would, then method B is get into vertex form. I'll just go ahead and say that, get into vertex form, like I did above. I don't know if that's the exact answer that they want, but it turns the horizontal compression into a vertical stretch. That vertex portion is not a requirement in any sort of way to get it to that if you use a table. But if you get into vertex form, then you know exactly where to go. I don't know if that's the method, but it sounds good to me. All right, number 7. Let g of x equal 1/3 times the absolute value of x minus 1 minus 2. Part A, describe the transformations from the graph of f of x to the graph of g. Part B, graph g. So this is more like numbers 1 through 4. There are just multiple parts to it. So that's all. So g of x equals 1/3 times the absolute value of x minus 1 minus 2. So let's do the description first. I'm fine with that. I just need to know how much to fit. So first, that 1/3 is A. That's a vertical compression. Vertically compress by a factor of 1/3. We also are going to translate 1 unit right and 2 units down. I can't spell right. The 1 unit right is H, 2 units down is K. Now, when I graph it, I'll do it based off the vertex. Let me get a graph to use. And then I'll use the 1/3 slope. Okay. Now I was going to say, hopefully we don't do a lot of graphs after this. We have piecewise functions after, so I think we have to. So 1 unit right, 2 units down is our vertex, 1, -2, and then up 1/3. Like that. Oh, that's green. And there's your graph. So those are probably more, if I were to test my students, those are more to be expected, not a single transformation, but multiple of them, describing and all. And that's number 7. Okay, we're going to move on to section 1.2. Now, I'm not hitting number 8 just yet, but I'm just getting us ready. So for section 1.2, you look at this portion where we are graphing piecewise functions. And piecewise functions have two different portions, or multiple portions, where it behaves differently on different parts of the domain. First, it's y equals 3/2 x plus 3. That's slope-intercept form. Slope of 3/2, y-intercept of 3, if x is less than or equal to 0. So when you see this graph, you start at y equals 3, and you go down 3, left 2, down 3, left 2. We don't go up 3, right 2 for this graph because it's only when x is less than or equal to 0. That basically to the left of 0. And including 0, that's why there's a closed circle on it. So we go down 3, right, left 2 to keep the slope positive and plot as much as we can fit within our window, and we get our graph. To the right of it, it's going to be graphed like y equals -2x, which is -2x plus 0. The y-intercept is 0, and we would go down 2, right 1, down 2, right 1, as far as we can within our window range. Now, we don't include 0 because x must be greater than 0. So anything to the right means an open circle on the y-axis itself, and then everything to the right of it after works. So they describe that, I believe, right there, and we're all good. The domain and range, the domain is all real numbers because we hit everything from negative to positive infinity. 0 is included right there, even though it's not right there. The range is y is less than 3. That helps more when you see the graph. On the graph, 3 is the highest value that's hit, and it hits every value below, including 0. Maybe not right here, but it hits y equals 0 right there. And since it goes down forever, you can see it goes left and right forever as well, which is another way to get the domain. So there's that one. We're going to look at number 8, where we're not graphing. We evaluate the function in the example when x equals 0 and when x equals 5. So on number 8, if you have the equation for the piecewise function, y equals 3/2 x plus 3 when x is less than or equal to 0, and y equals -2x when x is greater than 0. If we refer to this portion of it, we will do f of 0, which means substitute 0 for x and get the value out for y. We will not substitute it into either equation. We must do it in the one where 0 is included in the domain, which is the top equation, not the bottom one. So we see here that'll be 3/2 times 0 plus 3, or the y-intercept, which is 3. And that's the other point I want to make. I could have used the graph for this portion and pointed to it. This is when x is 0, y is 3, not 0, not the open circle, but the closed circle. So I can actually see that one on the graph as well, and I'm good to go, whether I substitute it or do the other one. They also ask for x equals 5. Now this, not visible, excuse me, this is not visible on the graph. X equals 5, here's 1, 2, 3, and 4, and it goes even down further than that, so you can't really see it. You could imagine what it is, but that's what the equations are for. So if you have it on your graph, great, and if you don't, of course, use the equations. 5 is greater than 0, so we substitute into the bottom equation. We do -2 times 5, -2x, and that's -10. And those are the evaluations. That's how you do them. That's number 8. I hope there are more questions than that, personally, for the section. So let's move on and see what we have next. Number 9 and 10. Graph the function, describe the domain and range. So now I'm going to do the graphs with you, and we're going to see what they do. So number 9, we get y equals absolute value, curly braces, x plus 6 if x is less than or equal to 0. We're once again on that. And -3x when x is greater than 0. So at least this one looks enough like the example that you could kind of follow along even if you had trouble the first time. I think it kind of allows you to do that. So we're going to go ahead and get this graph in. I'll first color code it blue and show you x plus 6 has a y-intercept of 6. And you would be rising and running 1 like this because of the slope, but it's only when x is less than or equal to 0. So we shouldn't go this way. We should go this way. Down 1, left 1. over and over again. Now, only when x is less than or equal to 0 means nothing to the right of 0. I'm going to get rid of those ones. X does include 0, so I'll put a closed circle on that like this. And I'm only going to be graphing this guy to the left. Is this blue still? Yeah. To the left that way. So it behaves like that graph, and if it behaves like it across the whole real number domain, I would have gone up to the right as well. But it doesn't, so I don't. So it's just for that. Negative 3x, yeah, this is a lot like the other graph. Negative 3x when x is greater than 0, that's negative 3x plus 0. So that's a y-intercept of 0. It doesn't include 0, open circle. And we're going to fall 3, run 1 to the right, and get these points only to the right of 0. So it looks like that. So that's the entire piecewise function, all in blue and green. If you have a single color, I'll go and turn it black now, it would just look like that. So there you go. There's number 9. Domain is all real numbers. If you refer to the graph or otherwise, it hits everything to the left of 0, everything to the right, including 0, and everything to the right of 0, left and right. The range is limited based on this being the highest value, 6, and it goes down. This is a lot like the example problem. They really wanted to lean into that a lot, I guess. Y is less than or equal to 6. We include 6, and we hit 0, not here, but over here. Okay, number 10. This one becomes a different looking problem, at least when it comes to stuff. We only have 2 parts of the piecewise. Piecewise functions can have more than just 2 parts. I'm noticing that we're not seeing anything on step functions, unless the word problem does it there. But I don't see anything on step functions in piecewise things. But you could have more than 2 equations. You could have 3. You could have 20. So if you want to see more examples, you'd probably want to look at my 1.2 video and find the ones that are different there. So when x is less than negative 4, we're going to graph it like y equals 4x plus 2. And when x is greater than or equal to negative 4, we're going to graph it like y equals 2x minus 6. So give me, I totally forgot how to, oh, there we go. So give me a graph. There we go. We're going to go ahead and start with the first one. This time we'll do this all in black. Y equals 4x plus 2 if x is less than or equal to negative 4. Now, this might not fit in my window range. I'm going to let you know that right now. Okay, I'm going to graph starting at 2. And because x is less than negative 4, I have to go all the way to when x is negative 4 here, which means I'm just going left. So I'll go down and left to keep my thing positive. Down 4 left 1 here. Down 4 left 1. Down 4 left 1. And my graph isn't tall enough for this, but we have to graph it, right? Yeah. Down 4 left 1 like this. And this is where I would start. Open circle down at x equals negative 4, y equals negative 14 all the way down here, and then another down 4 left 1 like this over and over. This is where the graph starts. So this isn't as fun of a graph when it comes to your window range. My graph goes all the way down here, and it doesn't show up anywhere else up here. I wish I could give them another problem, or they could give me a proper window range for it. If the other one is just as bad, I can't tell. I don't think the other one's just as bad. If the other one was just as bad, I would give you a different kind of window thing, but I don't know. I'd have to come up with a graph thing that has it somewhere. I might have one that's tall enough. Let's see if I have one, because this looks stupid. Okay, maybe I do here. Give me 1 sec. I'm just going to let something... Here, I'll pause this. Give me a second. Okay, I am back, and I got something for you. And this actually might come in handy later. So I'm going to get rid of this. We'll do this again. The same idea. This still won't be great. We're not going to get many points out of this, but at least we'll have the starting part on there. I have graph paper that'll actually also be helpful for when we do exponential functions. Possibly having it this tall. I think we ran into a similar problem at the time. The one problem with this graph paper is that you don't see the numbers as a scale, but you can see little hash marks here, hopefully. So let's do that again. 4x plus 2. So at 2, I'll go down 4 over 1, down 4 over 1, down 4 over 1. This is negative 10, and down 4 over 1 is negative 14 right there. This is where I get an open circle. And again, down 4 over 1, this already even goes off the graph here, but at least I get one portion of it all the way down here. At least it still fits on the graph itself. And like I said, I killed two birds with one. And I'm going to erase all these. I get to kill two birds with one stone and use this for exponential functions later. So there's at least the beginning of it. The other part of this, when x is greater than or equal to negative 4, is graphed like y equals 2x minus 6. So negative 6 is here. Oh, you know what? This is helpful to have it for this graph. So what is it? Positive or negative? Positive. So I get to go down to left 1 over and over like this, and it actually hits this point like that. Boom. And I get to close the circle because this is when x is greater than or equal to negative 4, and it includes that point there. So what was open is now included on the other part of the graph. And I get to go up to right 1 for the rest of the graph on this side. So this one seems to be reasonable with what we have. I'll go ahead and attach this graph paper in the description section if you need it, but it's just, I probably will anyway for the exponential part. It's just like that. They could have been a little better with y-intercepts and finding one, because they can't assume people have this kind of graph paper or are going to waste their paper on a grid like that the whole way. But that is number 10. The domain is once again all real numbers. This hits everything left and right forever. And if you notice, the range is also all real numbers. This hits everything up and down, including negative 14, which is the part that's hit right there. Okay, that's number 10. Let's move forward. Number 11. Write the absolute value function as a piecewise function. So we're doing it for all of these. Okay. Now, I'm not going to graph these as a whole, but I want to get the concept of what's happening. So what we have on these is, if you imagine this is a vertex at 0, 15, and we go up 1 over 1 slope like that. So we need a piecewise function that covers the left portion of it and the right portion of it, because these parts behave differently on one part and the other. And this is a nice way of kind of leading into what the absolute value graphs would have looked like. So to the left, we can do, remember, the slope, even though it's up 1 over 1, the slope is kind of 1-ish. It's negative 1 on one side. Up 1, left 1 is negative. So y equals negative x, and that y-intercept is plus 15, right? That's where x is, I could say, less than 0, for example. And then it's greater than 0 on the other side. Y equals positive x plus 15 when x is greater than or equal to 0, like that. So it hits both, but I have to put the equal to on one of them. You don't put it on both. And I have to put it on one of them to close the circle up. The slope is 1 as it goes up and over, 1. But negative slope there, and it hits the same y-intercept for both. And that would be number 11's answer. That's actually it on that one. Some of them can get a little trickier, all depending on translations that we have. Number 12, I think, is an example of something that's a little different. So I do want to, once again, do a rough sketch at the very least. Graphing these isn't terrible. Like, maybe you should, practice graphing it. Meanwhile, if we have trouble tracking where it goes, I could do it with you. But this one here, this is graphed 5 to the left. So 1, 2, 3, 4, 5 like that. And it rises 4 and runs 1. So it's a little sharper like this. So we have to get this portion and this portion. Now, the tricky part about this is because we're writing these in slope-intercept form, we need to find out the y-intercepts of both of these. So this is at 5 to the left. It's at negative 5. That's an x-intercept, not a y-intercept. You would need to figure out how much you're doing rise and run. There are other ways you can say this, but I'm going to leave it there. Actually, there is a pretty easy way to do it that I can show. Maybe I will. But how you rise 4, run 1, 5 times to get to its y-intercept. How many times are you rising? Sorry, 5 times. So how much is that? You're rising up 20. So rise 4, run 1, that's 4. Rise 4, run 1, that's 8. Boom, 12, 16, 20. So on one side of it, you go up 20. On the other side, you go down 20. Down 4, right 1. It's negative 4, negative 8, negative 12, negative 16, negative 20. So this would end up looking like, for the negative one, because you do the left one first, negative 4x minus 20, because it's got a negative slope and it hits negative 20. That's when x is, I can say, less than or equal to negative 5, for example. and then positive 4x plus 20 when x is greater than negative 5. Now, one thing I didn't do last time, and I'll do it this time here, is maybe you want to write it in slope-intercept form in the end, but it doesn't have to start that way. You could write it in, we use that AHK thing, right? The A times the absolute value of x minus h plus k to refer to translations for a vertex. It doesn't have to be for absolute value functions. This can be for any function. It can be for a linear function like this. X minus h, boom, plus k. And you start at some hk that's not your y-intercept, like this. So my point is, this point on the graph can be graphed for this line as y equals negative 4 times the quantity x plus 5. Just like that. This is this line. I mean, if you continue it, this is that line. What's nice about this is what happens when I distribute negative 4. I get negative 4x minus 20. On the other hand, the other one has a slope of positive 4 at the same point, boom, x plus 5 like that. And what happens when I distribute 4 into here? I get 4x plus 20. So you can come up with that 20 given this AHK business. You can still do there's no k is 0. It's at negative 5, 0. But you can still use that concept on this, and it's not lost. Maybe I can try it for some of the other problems. Like number 13. Let's see what they do for us here. You absolutely could for this one. It's all about just turning your slope negative. And honestly, that's probably what they're asking you to do. I don't read much in the book. I don't read anything in the book. So they're probably asking you, yeah, just turn the absolute value signs into parentheses and distribute and go, because this graph, absolute value, makes it a V shape. Without it as parentheses, it's just a line with a slope of 2, or if you make it negative 2. So if I were to not do the graph at all, and go raw, I would do this. Because it's a right side up graph, I have a negative slope going to the left, and it would look like this in raw form. By the way, this vertex is at negative 2, negative 3. So this is when x is less than negative 2. And then when x is greater than negative 2, it's a positive one going this way. If you recognize what we're doing, this is what they are. And this is proper. This could be an answer, and it would totally work. If we distributed stuff, however, in combined like terms, what would it look like? Negative 2x minus 4 minus 3, which is negative 2x minus 7. Negative 2x minus 7. Don't worry, I'll do it the other way as well, because you've probably seen a couple of those. Distribute 2 into here. 2x plus 4 minus 3 is 2x plus 1. 4 minus 3 is 1. So 2x plus 1. And boom, I'm done. I actually got him that way. And honestly, like I said, this is probably the way they want you to do it. Or you can graph it. So if I graphed it, again, vertex would be at negative 2, negative 3. You'd rise 2, run 1, boom, 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 and go this way here. So this left one has that slope of negative 2. From negative 3, from negative 2, negative 3, you go down 2, right 1 twice. Down 2, right 1, that's negative 1, negative 5. Down 2, right 1, 0, negative 7. Boom. Here, up 2, right 1, you're at, where are we at? Negative 1, negative 1. Up 2, right 1, 0, comma 1. Boom, you're right there. I didn't scale them, but I'm giving you the idea of what happens. How many times you count up and over and down and over. And that would be the answer. Okay, those are those 3. Let's keep going. Number 14. We're only in section 1, 2. You are organizing a school fair and rent a popcorn machine for 3 days. The rental company charges $65 for the first day and $35 for each additional day. Write and graph a step function. So this is a step function. Write and graph a step function that represents the relationship between the number x of days and the total cost y in dollars of renting the popcorn machine. So they do say for 3 days. So we get to do this 3 times. I'm wondering if doing the graph, this graph I'm not going to use graph paper for. I'm just going to kind of draw axes and work it out as a rough thing. So for 14, let's kind of draw the graph first and see how the equations work as a result, or the other. Either way is fine here if I describe it one way or the other, but it's very much a first quadrant graph, and it's just going to be a rough sketch. So $65 for the first day, rent a popcorn machine. So on that first day, you're renting. I'm trying to decide. I guess if you don't rent it at all, that's at x equals 0. You haven't rented, so I'm going to do an open circle at $65. And 1 day through, you're going to have spent the $65 for the entire day up through the end of the day. Like that. For day two, it's $35 more, plus 35 is $100. So here, I guess you can, are they asking us to graph? They're asking us to graph. This could, I don't know whether they'd want an open circle here versus the other way. I can argue both ways. Like, for instance, day two doesn't start until you start doing part of the day, if that makes sense. So it's very possible, I'm just going to let you guys know, it's very possible that they reverse the open and closed circle thing. I imagine because day zero, like that, I don't rent the popcorn machine at all, and I do it for the full day at the end of day one. I've only paid $65. Once day two's thing begins, I've paid the extra $35 like that. That's my go-to on this. And I guess there are only 3 lines. And day three, day one, day two, day three, another $35, so $135, like so. And then we have the open circle right here and close it off till the end of day three. I imagine that's the way that it would go. That seems to make more sense to me, personally. Step function represents X days. Okay, so here we go. We're going to say Y, the cost. This is where we get to write 3 equations. They're all constants. This is how step functions work. It's 65 for the first day. That's between 0. Ooh, we get to do compound inequalities too. Between 0 and 1 for the whole day. $35 later, you're spending $100. That's from day 1, or for day 1, I should say, up until day 2. I guess that looks kind of weird, but that's okay. And then $135 from day 2 into day 3. Anyway, if there's someone who says, no, this is wrong, teacher says no, answer key says no, the only change would be flipping these and putting a less than or equal to, boom, there, and then a less than, boom, right there. Otherwise, this looks pretty good to me. And that is section 1.2 on piecewise functions and step functions. Let's move on to section 1.3 on inverse of a function. Find the inverse of f of x equals 1/3 x minus 2, then graph the function and its inverse. So first we turn f of x into y. F of x becomes y right here. And then we swap x and y. That's what this is the inverse step. But when we want to write this final one, and they use g of x, I'm going to use this inverse notation that looks like that. Sorry, I'm using my mouse for this, based on where it is on my computer. I'm going to use inverse notation like that to state it's the inverse of the function, f. But they solve for y in the end. They swap x and y, they add 2 to both sides, and multiply both sides by 3. Notice how the whole set gets multiplied by 3, and that's the inverse. When you graph them, you'll notice that the x's and y's just swapped with each other. Notice this dotted line. This is the equation of the line y equals x. And take a look at this point on f that's 0, -2. There's a point on g that's -2, 0. The x's and y's swapped. There aren't very many other points that we can hit that are integers other than right at -3, -3. When you swap them, it's still -3, -3. So we're going to see other versions of it. I'm sure we're going to be asked to graph the function and its inverse, just like this. In the second example, this is not a second example. This is number 15. We have to do number 15. Okay, number 15. Find the inverse of the relation there. So let's do it. So number 15, we have 1 -10, 3 -4, 5 -4, or 5 +4, 7 14, and 9 26. The inverse swaps the x's and y's. That's all you do. From 1 -10, we'll have -10 1. From 3 -4, you'll have -4 3. From 5 4, you'll have 4 5. From 7 14, you'll have 14 7. And from 9 26, you'll have 26 9. I'm glad they don't ask you to graph it. But that's number 15. Now, we'll have to graph the others with lines, and I'm fine with that. Number 16. F of x equals 3/4 x. We are going to find, 16, 17, and 18, we're going to find the inverse of the function, then graph the function and its inverse. Kind of like the example. Exactly like the example. F of x equals 3/4 x. First thing you want to do is turn this into a y for flexibility purposes, and the fact that this may no longer be a function, and y is no longer going to be a function of x when you swap. You take the inverse, we're going to swap x with y. Now we're going to solve for y. If you have trouble with this fraction, we could divide both sides by 3/4, but we don't write it like that. We're going to multiply both sides by its reciprocal, 4/3. In a single step, 4 divided by 4 is 1, 3 divided by 3 is 1. You're left with the y equals, and it looks like 4/3 x. Y equals 4/3 x, or the way I'm going to write it, inverse, I'm going to graph right there. 4/3 x, or inverse of f is 4/3 x. So they ask you to graph the function and its inverse, and I'm also going to have that little, let me steal a graph axis here. I'm also going to have the little dotted line for y equals x on this to show the reflection bit. Okay, here we go. So let's start with graphing f of x equals 3/4 x, this guy. So 3/4 x plus 0. So start at 0, 0, rise 3, run 4, over and over in a positive manner, and fall 3, run 4 to the left. Like that. And we'll get, with arrows, this guy. Right there. That's the original. The green will be the new, the inverse. Also has a y-intercept of 0, and we're going to rise 4, run 3, like so. So you can sense the inverse within the slope itself. I mean, it's going to make sense for all the ones that we do. But instead of rise 3, run 4, we rise 4, run 3. X's and Y's are literally swapping before your very eyes. There's nothing else that you need to see in the equation itself. That's kind of it. So we're noticing that right there and now. There's the function and its inverse. And if I did graph the line y equals x, it would look like that. That's a 1x plus 0, and you can see the reflections of each piece. So if there's a point right here, that point is 6, 8. There's a point on this one that is 8, 6. 6, 8, 8, 6, etc. They are inverses of each other. You swap the x and y. That's the idea. And finding the inverse does that, solving for y again and being able to graph. That's number 16. We'll do it for the other two as well. Number 17. F of x, not even halfway done. We go to 33. F of x equals negative 5x plus 10. All right, y equals negative 5x plus 10. Take its inverse. X equals negative 5y plus 10. I imagine the others will go faster because I don't have to graph and such. This is where we hit exponential properties, I think, in a bit. Solve for y. I'm going to subtract 10 from both sides. And then I got to divide both sides by negative 5. So I get x minus 10 all over negative 5. Now, there's a lot I still kind of got to do with this as far as breakdown. That's x over negative 5 minus 10 over negative 5. I really want that slope-intercept form. So that's negative 1/5 x plus 2. And this is maybe at the time where I want to write it as inverse notation. Inverse of f. Boom, like that. So this is what the inverse graph is, and we're going to go ahead and draw both of them, sketch both of these on the same graph, the original and the new. Let's take a look. So the original in le bleu, 10 is the y-intercept, and we'll go down 5 over 1. If you're okay with this, I'm going to go pretty fast on that. Oh, I still have the dotted line feature. Give me 1 second. There we go. And then this other one is negative 1/5 x plus 2. So 2 is the y-intercept, and down 1, right 5, like this. I'll once again remind you that there are points that are reflections of each other, starting with the y-intercept of this guy and the x-intercept of the other guy. The y-intercept here was 0, 2, as you saw that. How does that relate to 10? Not so much. It relates to its x-intercept, 2, 0. Those are the same, and it reflects across that line y equals x. Excuse me. That was green. All right, that's number 17. We don't have to do anything else with those, right? It just graph, no domain range, anything like that. Number 18. F of x equals negative 2/5 x plus 6. 18. F of x equals... Okay, here we go. Turn into y equals... Whoops. swap x and y, and then solve for y again. So get this y by itself, subtract 6 from both sides. That's an inverse step from addition. And I don't know if you guys would be comfortable doing this in one step or two. I'm going to do this in 2 steps. It's dividing by 5, right? So we could say, all right, dividing by 5, let's multiply both sides by 5. I don't know how comfortable you are by multiplying both sides by -5/2 and dealing with the fraction. So I'll do 2 things. I'll do one thing at a time. So now I have -2y. I'm going to write this on the left. -2y equals, and I got 5x minus 30. I'm going to go ahead and put it like that. And now I can divide both sides by -2. So when I do that, remember I can split the fraction up. This becomes, we can do this now as 1, -5/2 x. And -30 over -2 is positive 15. So plus 15, like that. And there's your equation. So we're now going to graph both of these. The thing that you might look at with this and say, especially when my graph axes are not that large for 15, you say, oh, I can't fit the 15. How am I going to graph that? Well, let's start with the original, -2/5 x plus 6, because I can fit that one. So 6 is here. I can go down to right 5, like that, and up to left 5. So I get my first graph. Now, the second graph, remember, is just an inverse of this. I can either graph it based off my equation, which I'll use a part of it, but I can use any other part of this to make sense of it. Remember, I have a point 0, 6 here. The inverse will have a point 6, 0, swapping x and y. You don't have to use the y-intercept. You can use any point on a graph and apply the slope as long as it's on the line. And 6, 0 should be on it because it's an inverse. And I can go down 5, right 2, like this from that point. The same thing applies. I do it in my video for section 1.3, and this would hit 15 up there, if I could fit it. But I did this in the other thing as well. We had some fraction y-intercepts on some other problems. You know, like it could be plus, 2/3, whatever it is. And the same thing applies. If you don't like a fraction y-intercept, and especially dealing with the slope on the fraction y-intercept, or if it fits out of your window range, or a combination of both, use another point from your original by swapping it. You know, here's 5, 4. There's a point that's 4, 5. Here's 10, 2. There's a point that's 2, 10. Things like that, and then apply your slope. Or plot them all. Plot all the inverses with it, but they still need you to find the equation to confirm that it works. Last one on 1.3 is number 19. In bowling, a handicap is an adjustment to a bowler's score to even out differences in ability levels. In a particular league, you can find a bowler's handicap H by using the formula here, where A is the bowler's average. Solve the formula for A, then find the bowler's average when the bowler's handicap is 28. So they're just using concepts of inverse. They explain what a handicap is, things like that. Like, oh, we'll start you with a score of 40 because this other person who's more skilled is going to, catch up to you. So we have an equation that's H. It's not X and Y, but they are 2 variables where H is currently solved for, and then they want you to solve for A. So I'm not swapping H and A, as in like actually replacing them. The whole goal of doing that is so we can graph them together on the same thing, a function and its inverse. This is a formula for a bowler's handicap based on a bowler's average, some other bowler's average, I guess. You can find out someone else's handicap or this bowler's average. Now, if we solve for A instead, we can determine their handicap. If we solve for A, we can use their handicap to determine what a bowler's average is. It's the other way. So I'm going to start by dividing both sides by 0.8. And I don't know if I love writing that way. I don't love decimals in my thing. But let's do it. I might turn it into a fraction later. Divide both sides by 0.8. Now I have 210 minus A. I'll write it the other way. H over 0.8 equals 210 minus A. I can subtract 210 from both sides. And then I can, I'm going to do it the other way. I can add A to both sides. I'm going to do plus A, and I'm going to subtract this guy over. I'm going to subtract that guy over. So I'll get A equals 210 minus H over 0.8. So here's one version of it. I say one version. So 0.8 is 4/5, And when you divide by 4/5, you get 5/4. So I'm wondering if I want to write that as 5/4 h. I'll keep it like that. That's fine. So here's a that's solved for. Now, find the bowler's average when the bowler's handicap is 28. Now, if I substitute 28 in for h, I'll get some answer. So a is 210 minus 28 over 0.8. And this is where I got to use the calculator. I thought I had it popped up. Maybe I don't. Maybe I only thought about it. Never popped it up. So I'm not going to show you my calculator, but I'm getting mine on my computer here, and then I'm going to work it out. So 210 minus 28 divided by 0.8. And I'm getting 175. So A is 175. And that's the bowler average. So that's just a score. That's points, I guess, if you will. Normally I like context, but I don't know what to say. Points? Points? Sure. Score. 175 score, if you will. I think they use points in bowling. All right. That's the end of section 1.3 on inverses. Now we go to 1.4, 1.5, and 1.6. And I imagine 1.4 and 1.5 go kind of faster. If you've seen my processes, then you know what they look like. So let's take a look at properties of exponents. They're asking to simplify this guy as an example and write the answer using positive exponents. A negative exponent is a way of saying dividing. So if I turn negative 4 into positive 4, that's by taking x in the numerator and putting it in the denominator, and taking 4 in the denominator and putting it in the numerator. I personally would turn that exponent positive first and flip the fraction, but either or is fine. You get to the same amount. And evaluate. 4 to the 4th is 256 divided by x to the 4th, and it's simplified. So that's the idea behind what we do on these things. I know that didn't cover everything. You can't assume to go straight into this and learn every part about this. You got to try some of the ones from the section. So number 20, we have y cubed times y to the negative 5th, and they're asking us to simplify. Another property that's involved here is these exponents add when you keep the same base. Not going to sit here and explaining why, but 3 plus negative 5 is 3 minus 5, which is negative 2. Only positive exponents, though. Y to the negative second power is 1 over y squared, and that's simplified. 21. We have x to the 4th divided by x to the 7th. Now, the way that they would kind of teach it to you is you keep the base and subtract the exponents. So x to the 4 minus 7 is negative 3rd. As a positive, that's 1 over x cubed. That's fine. What you're going to see me do when problems get a little trickier, if they get that big, is you'll see me take x to the 4th over x to the 7th, and I'll say, we're going to divide out 4 pairs of x's multiplied on top and bottom. So I'm going to remove all 4 x's from here. I'm just left with a 1. There's still something in the numerator. And I remove 4 x's from the bottom. I'm left with 3. And that's where I get there. You'll see why, if it gets really cluttered, why that might be a nice thing to do, especially if we turn into these. It's not terrible to go this way if you know the placement of where they go, but a lot of people don't. And if you have trouble subtracting with and from negatives instead of positives. So anyway, that's just something that comes into form. Number 22. X to the 0 times y squared, quantity cubed. It looks like they're not trying to get complex problems. They're just trying to hit every property base that we're going to have. So x's and y's can't like mingle with each other. Like I don't add these exponents. They stay separate. And by the way, x to the 0 power is just 1. And 1 times y squared would just be y squared. I can happily just get rid of that. We're looking at y squared cubed. And what happens with these two guys, a power to a power, you go ahead and you multiply those exponents. You get y to the 6th. By the way, x to the 0 to the 3rd would have been x to the 0 times 3, which would still be x to the 0. That's why that still becomes that. Or, as this is just a 1, 1 cubed is still 1. That's why this still stays as y to the 6th. That's why it can be ignored in a way. And then 23, I kind of hope there are more problems than just these on this set. We'll see, or how complicated they get. We have 2x squared over 5y to the 4th. Whoa. All raised to the negative second power. Definitely not the biggest kind of problem that you'll see, at least depending on who's giving them to. I'm going to deal with that negative exponent first and just turn it positive by flipping this fraction. Again, this goes kind of against what the book did, which was apply the negative 2 first. I want to turn things positive as soon as possible if I'm dealing with fractions, personally. Now, I'm going to kind of write this next step out. I'm going to square everything in here. Anything that's a product or division, quotient. I'm going to square 5. I'm going to square y to the 4th. I'm going to square 2, and I'm going to square x squared. Everything gets squared. That's kind of how the property works for everything in the product. 5 squared is 25. Y to the 4th squared is not y to the 16th, but y to the 8th. 4 multiplies with 2. 2 squared is 4. 2 times itself. And x squared is also x to the 4th. But that's because it's this 2 times this 2. It's not the same thing for that. 25 over 4 can't reduce. I would have done that earlier if I could have. And y's and x's can't reduce or work with each other. I would have done that earlier if I could have as well. That would just be the final result. All positive exponents, by the way. Okay, let's see what they do on the other side. Oh, that's it on 1, 4. Okay, that's it. I kind of wanted more because they go fast, but also I wanted to hit problems that might do more. But what does more is just more of it. So they don't become harder, they just become more. It just depends on if you can stay focused on them. The one kind of problem I wanted to see, and I probably could have shown here, is whenever I have a negative exponent in one of these, I'll take it and move it down to turn it positive first or something like that. Okay, radicals and rational exponents, section 1.5. Rational exponents are fractional exponents. 512 to the 1/3 power. That 3 in the denominator of the exponent acts as the root of your thing. The 1/3 becomes the cube root of 512 to the 1st power, if you will. And the cube root of 512 is 8, something that either you can use a calculator for, but if you can't, there are other versions of just knowledge of it, but it is 8 times itself. It's 8 cubed. 512 is 8 cubed, so the cube root of 512 is 8. So we're going to evaluate some of these. We got the cube root of 8, which asks what number times itself 3 times is 8, and that's 2. I think they're going to stick with perfect power values, so perfect cubes, perfect fourths, and things like that. So we'll see. Number 25 says that's the answer. Number 25 says the 5th root of negative 243. Now, if this was a square root, 4th root, 6th root, if this was an even root, you wouldn't get a real answer here. You cannot take the square root of a negative, even root of a negative, because any negative times itself would be positive. There's no way to get that result. 5th root is fine. It's an odd root. 5 negatives multiplied becomes negative. That means this answer will also be negative. What number times itself 5 times is 243? It's actually 3. So negative 3 to the 5th power would have given you negative 243, and the 5th root, therefore, is that. So that's just evaluating radicals. Let's look at the ones with rationals, and they're really slimming it down on the review. We'll see how the chapter test goes in my next video when I make it. 625 to the 3/4 power. This time, let's convert to radical form. That becomes the 4th root of 625 cubed. But I want to do the cubed last. I don't know what 625 cubed is. I'm not trying to use a calculator for that, and even if it was that big, I wouldn't know how to do its 4th root. But I do know the 4th root of 625. Even if you don't, I do. It is 5. Anything that ends in 5 will have to be some form of 5, so either 5 or 15 or whatever, but it's 5. And 5 cubed, right, that's what's next. This part is 5. 5 cubed is 125. And then lastly, number 27, we have, oh, here's a good example, negative 25 to the 1/2 power. Now, I want to remind you that we are not taking half of negative 25. The answer is not negative 12. We're raising to the 1/2 power, which means we're taking the 2nd root of negative 25 as if it were raised to the 1st power. The 2nd root is also known as the square root. They often don't write the 2 there, so make sure that you know that if you have this, it also means to the 1/2 power. The square root of negative 25. It's not negative 5, because negative 5 times negative 5 is positive 25. There is no real answer here. There's no real solution. Not possible. No real value. You cannot evaluate this one. You can try it in the calculator even. Just put parentheses around the negative 25, raise it to the 0.5 power, to the 1/2 power. It'll give you that. Unless you type it in wrong, it'll tell you there's a domain error or something of that sort. All right, and the last set from section 1.6, we'll see we have 6 more problems to go and see where we go from there. I remember I might have to use the calculator in some of these, so we'll take a look. Determine whether the function y equals 3 to the x represents exponential growth or decay. These are examples. Then graph the function. So 3 to the x will be exponential growth because the base 3 is greater than 1. You're multiplying by 3 each time x increases by 1. That makes it growth. It's positive growth, by the way. And here's the appearance of the graph. They use a table. If you've seen what I've done before, I'm going to start from what is essentially an a value, which is our y-intercept. This a value is 1. It's 1 times 3 to the x power. And then I'm going to multiply by 3 over and over to the right and divide by 3 over and over to the left. They give a good example, and you can plug values in using your exponential properties. But if you learn them to graph, we can do that. So they draw a graph, smooth curve, blah, blah, blah. The next question says, rewrite the function to determine whether it represents exponential growth or decay. Identify the percent rate of change. Now, these questions are asking you to do a little bit more because they need you to get it in a form where it's raised only to the t power, where there's only the variable in the exponent. And in order to do that, you have to use some of the exponential properties from before. 10 times 0.65 to the t8th power. T8 is t over 8, or 1/8 times t. 1/8 times t can be split up into the power of a power, like this. It goes kind of reverse what we had. So therefore, we can do 0.65 to the 1/8 power, which is also the 8th root of 0.65, which rounds, you can see the approximation, it rounds to 0.95. That 10 stays on the outside and doesn't affect it, and there's a t there. So it goes to show that it's still decay because 0.95 is less than 1, and that's what you see there. But the percentage change asks you how far away from 1 is this number. 1 minus 0.95 would give you 0.05, and 0.05 is the decimal equivalent of 5%. This is a 5% decay because this is 95% of your value. This would make more sense if you saw this stuff in section 1.6. I'm just going through the example, and I'm going to go through the problems. So let's go ahead. This is where I'm going to use that other graph. So give me one moment. I'm going to pause and find the other graph paper. Okay, I found one. There we go. All right. So I'm going to use these ones here because exponential graphs can be significantly taller. They're only, I think they only go one direction. I think they only go positive on these graphs, so that's okay. They don't do too much on these actually. Okay, number 28. We have f of x equals 1/3 to the x power. So when x is 0, y is 1. That's what I mentioned when I was saying y-intercept. It's 1 times 1/3 to the x power, which means this y-intercept is 1, like that. When x is 1, y is 1/3, which is a third of 1. And then you multiply by another third to get 1/9 when x is 2. So I'm not making the table, so to speak, but I'm giving you the idea and I'm saying them out loud. So 1/3 is y, 1/9 is y. You multiply by 1/3 going to the right, and you divide by 1/3 going to the left. So going to the left, dividing by 1/3 is the same as multiplying by 3. We triple our values. So times 3 is 3, times 3 is 9, and times 3 would be 27, which fits off the graph. They say draw a smooth curve. I'm going to go ahead and try the best I can. Hopefully I don't have to redo. And this gets closer to 0 like this. This is where you feature what's known as a horizontal asymptote. This dotted line right here that says we will not cross this thing at all. I don't think the book talks about it, but it approaches 0 more closely. It never touches 0 and it never goes negative. That's the idea of this graph. And that's all they ask us to do. Oh, decay. This is exponential decay. It's positive exponential decay. All of these will be positive because the a's will be above 1. If you see some other videos of mine of old, you'll see where I do some other ones. Find one called Graphing Basic Exponential Functions. I think it's called that. Graphing Basic Exponential Functions. You'll see other versions beyond these if you're taught them. Number 29. Y equals 5 to the x power. Once again, it's 1 times 5 to the x power, as in the y-intercept is 1. If you substituted 0 for x, you'd get 1 for y. So once again, we're going to start right there. Every time x increases by 1, we'll multiply by 5. That makes this exponential growth. So times 5, boom. Times 5 would be 25. I already can't fit that, and that's going to shoot way up there. Divided by 5 is 1/5. So much for having this tall graph stuff. These are really the only reasonable points that I think I can show you and plot. But it goes sharp that way pretty well. Don't make it cross x equals 2 if you have this kind of graph height. Because it should hit at 2,25. And I didn't reach 25, so I better not reach 2 for x either. It's going to look like that. This is positive exponential growth. They're not asking for domain and range, are they? Oh, percent rate of change. I'm sorry. Let me go back on this one really fast. On number 28. I didn't see these questions. Identify percent rate of change. 1/3. Sorry about this. 1/3 is about 0.33. Right? It's 0.3 repeating. Because it's a decay, we're trying to figure out how far away this is from 1. 1 minus 0.33 is 0.67, which means this thing decays 67%. 67% decay rate. If you're taking 33% of something, you're losing 67% of something. This isn't about. I could say 66.6 repeating percent. This is just an approximation. They gave us 1/3, so I have to go by the approximation. This 5, this one's a little interesting to mention. As far as, so it's a growth rate, right? There's a growth. 5 is 1 plus 4. And that sounds weird to say because we're trying to figure out how far away it is from 1, right? 5 minus 1. So let's see. 5 is 1 plus 4. It sounds dumb, but what we're saying is if you take 100% of something, 5 is 500% of something. How much more is 500% from 100%? It's 400% right there. This is a 400% growth rate. You're making something 400% more than it was before. 500% of and 400% more. Those are two different words, like English-wise, but that's what they are. See, if you grow something 100%, you've doubled your amount, right? Hopefully that makes sense there. Anyway, there's that one. Number 30. Now let's go to number 30. Where we're normal with decimals again. Hey, that's a question. It's important to know. F of x equals 0.2 to the x power. All right, so here we go.
All right, so
0.2 to the x. Y-intercept of 1. You know what 0.2 is also? It's 1/5. And I bring that up because I want you to know that when I multiply by 0.2, it's also multiplying by 1/5, which means I go down here. And when I divide by 0.2, that's the same as multiplying by 5. This is an inverse of the last graph that we just saw. This one here, which was times 5 going to the right. This is times 5 going to the left. And divided by 5 going to the right. So the same kind of idea. I would have hit -2, 25, but I can't fit it on the graph. So I'm going to go ahead and plot this here. Now you're going to see a different kind of change in the rate and such. This is a positive exponential decay. Exponential decay. And this decay rate, how far away is 20% from 100%? It's 80% away, 0.8. 80% decay rate. Like that. So 400% growth rate versus 80% decay rate. 5 times more versus 5 times less. I know those numbers, you can't tell based on seeing those numbers, but that's actually how it works. Okay, last 3, numbers 31 to 33. Rewrite the function to determine whether it represents exponential growth or decay. Then identify the percent rate of change. So number 31, we have f of t equals 4 times 1.25 to the t plus 3 power. Okay, so here's the concept of this one. I am, t plus 3 means you're multiplying two things of the same base, like two 1.25s. So 4 is multiplying by 1.25 to the t times 1.25 to the third. That's what makes those two things add, the two exponents add there. But 1.25 to the third I can evaluate as an actual number, and I can even multiply it with the 4. So instead, I want to think of it more as 4 times 1.25 cubed. This will eventually become a single value. And then over here, I'm going to have 1.25 to the t, which honestly matters more. They say rewrite it to determine something. I could be done right here and just tell you all about this part right here. But this becomes something as well. So I'm going to go ahead and figure that out. Again, you can't see it on my calculator, but 4 times 1.25 cubed, I'm getting 7.8125. And as long as the number's exact, I'm not going to round it. So that's 7.8125 times 1.25 to the t power. There's kind of a proper version of that rewrite. It's not the final answer. We're going to determine whether it represents exponential growth or decay. It's all about this value. This value is more than 1, so it's going to be exponential growth. And identify percent rate of change. How far away is this number from 1? It's 0.25 away, which makes it 25% growth rate. And that's what we do. That's why I was saying at this stage, I'm good. This number didn't matter for any of it, but I want to get a rewrite there. Maybe it will matter later, or maybe they ask you for the function. So that's 31. Number 32. Y equals 1.06 to the 8t power. Now, I should also mention, before I do this one, this 1.25 was here the entire time. Could have we answered it from the beginning? Sort of. You'd have to know what these things are doing here. This number is about to change on us. You saw it in the example. This number changed from 0.65 to 0.95. This one's about to change as well for the very reason that this is also 1.06 to the 8th power raised to the t power. Keep in mind that 8t means 8 times t, and that's a product of your two exponents, which is power of a power. If I rewrite this, so this is my b value, and it's raised to some variable, then I'll have that other form. So 1.06 to the 8th power, it's not going to be pretty. According to them, they're only rounding to 2 decimal places, so I'm going to do the same. This rounds, it's 1.593, etc. So that's around 1.60. It rounds at 1.60 to the, 1.59. I can't round. 1.59 to the t power, like that. So that's the approximation of the model. I could use more decimals, but I'm not going to. This goes kind of long. So it's once again a growth because this number is more than 1. But the growth isn't just, how far away was this from 1? That's a 6% growth. It's not that because this does it several times throughout the t. It's 59% growth. 59% growth. It's that far away from our 100%. And that is that guy. And the last problem. You're here for the last problem. Congratulations. Number 33. F of t equals 6 times 0.84 to the t minus 4 power. I think this one will be more like number 31. So I think that 0.84 remains. I think. So the t minus 4 power. The difference is how that t minus 4 works with this. That's equivalent to doing 6 times 0.84 to the t divided by 0.84 to the 4th. That's where these two would subtract. So once again, it's one of those things where you want to use this more with the 6. I'll divide the 6 by 0.84 to the 4th power to get that value. But this 0.84t to the t power remains like this. So I could answer the question based off this part right here. That doesn't change. This guy here, let's evaluate what that is. 6 divided by, it's probably something close to 6. 0.84 to the 4th. Oh, never mind. I must have been, I was misthinking how that works. I was thinking the 4th root of 0.84. My bad. It's, I'm going to write just it's 12.05. I'm going to write about 12.05 times 0.84 to the t. That part doesn't matter as much. What does matter is the 0.84. Once again, that makes it a decay. And 0.84 is 0.16 away from 1. That makes it a 16% decay rate. 84% is 16% away from 100%. It's 16% loss. And that would be the final one, making sure that's all it is. And that's all we have, guys. That ought to do it. This is a review of all the things with some of the examples that they had put together for us. The next time we do this, we're going to be looking at, I believe, what's called a chapter test, which doesn't have review things before. I think we just got to dive straight into the problems at that point. I just got to do them, give them to you, see how they are, see how you did. As a chapter test, that's probably how you practice. Practice and take a look. That'll do it. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.